Okay, so thank you very much for the introduction, and hello everyone. So when the user is immersed in a virtual reality application, and in this application the user's real hand is supposed to move in a different way than the virtual hand, we can use a technique that we commonly call hand redirection. Now in hand redirection, warping algorithms introduce a non-one-to-one mapping from the real hand position to the virtual hand that is shown to the user and offset the virtual hand from the real hand position. Now, when the user tries to reach for a virtual target, the user has to then compensate for this mismatch and adapt the real hand trajectory accordingly. We have seen the technique of real virtual hand offsets already in the talks before, and it has been shown that hand redirection can improve the scalability of interacting with passive props, for example by implementing techniques like redirected touching or haptic retargeting. And in the work that I'm going to present now, we try to contribute to the quantification of hand redirection as a technique itself and try to derive the order of magnitude of hand redirection that can go unnoticed by users even in worst case application scenarios. And in the past, researchers have already investigated the detectability of real virtual hand offsets, for example, when displaying a real and an offset virtual fingertip position to the user represented as abstract spheres, when the user is immersed in a game-like setting, or when the user is feeling a continuous haptic signal at the fingertip. And recently also researchers have investigated the tolerance thresholds, asking users about how much hand redirection they would actually tolerate in a haptic retargeting application. Now, in the work that I'm presenting here, we were really interested in the detectability of hand redirection, especially of fixed angular offsets, and we investigated a very conservative setup which resembles the worst case for unnoticeable hand redirection, as in our setup users were informed about the redirection and really paid attention on detecting the hand offsets because we wanted to derive lower bound thresholds. Moreover, we only display a realistic model of a virtual hand at the offset location, and we do not show the real hand location as it is common in haptic retargeting applications, and we do not involve any haptics at the fingertip. So to study hand redirection, we then split up redirection in 3 intuitive dimensions and we studied them separately. And this is offsets in the horizontal plane, in the vertical plane, and gain-based hand redirection. And for all 3 dimensions, we defined an algorithm that you can look up in detail in the paper. For the horizontal and vertical hand warping, the algorithm, it's kind of body warping algorithm, defines a warp origin. At this position, there's still a one-to-one mapping. Now, when the user moves the real hand then away from this warp origin, a fixed angular offset is applied and the virtual hand is offset in either the horizontal or the vertical plane. Similarly, for gain-based redirection, when the user's real hand moves away from the origin, a fixed gain factor is applied, scaling the movement of the virtual hand up or down so that the virtual hand moves faster or slower than the real hand. Now, to derive detection thresholds for these 3 techniques, we conducted a psychophysical experiment and we used an established methodology that was, for example, also used by the work of Steinecke before to derive detection thresholds for redirected walking. So we conducted a within subjects 2 alternative force choice experiment with 12 participants. And as we were interested in the user's motion of reaching out for something under redirection, like a retargeted prop or so, in our setup users were seated and also interacting in the desktop scale space in front of them, as we can see here in the picture. Now, during the experiment, users had to repeat a certain movement multiple times with different amounts of redirection applied. They always first had to reach a start position right in front of the head with the virtual fingertip. Here still a one-to-one mapping was applied. When reaching the start location, a target appeared in front of the start location, redirection was applied, and users had to reach this target with the virtual fingertip in around 3 to 4 seconds. And on the way, they of course had to compensate for the applied mismatch. And When reaching the virtual target, users then were asked the two alternative questions. So they had to state in which direction they thought the virtual hand was offset from the real hand position. We used the Vive system to implement the tracking, and users could then use a controller that they held in the second hand to answer the question. Now, to derive meaningful estimates, we investigated the redirection in 3 different setups, which were all 3 very conservative, as in every setup we told users about the redirection being applied, even about the type of redirection being applied, and we instructed them to pay specific attention on detecting the hand offset, as that was their main task in the experiment. And then in a first condition, we did not use any distraction, so we just let users focus on detecting the hand offset to create the most conservative setup we could think of, which maybe at the same time is kind of less realistic, because in an application you would probably try to distract from the redirection. However, here, users could just perform the movement and try to detect the hand offset. In a second condition, then we added auditory and vibrotactile distraction, because we wanted to see if a significant increase in distraction has a direct impact on the detection thresholds. And so here we still had a conservative scenario, but a kind of more realistic setup. And users in this case were distracted by the sound of a virtual bee flying around the head during redirection, and they felt vibrotactile feedback from 4 vibrotactile actuators that we placed at the head. And we activated them in synchronization with the sound. And in the third scenario, we tried to distract users using a visual and a dual task distraction. So here users had to look away from the hand at least once during redirection in order to read out a number that we displayed on a panel in front, and the experimenter then took note if the number was read correctly. So in total, we looked at these 3 different redirection dimensions in the 3 different scenarios, which sums up to 9 conditions. And in total, each participant contributed 246 samples to our threshold estimation. When we now look at the results, we can first look at the perceived distraction. So after each condition, we asked users how much they felt distracted from the main task on a 1 to 7 Likert scale. And as we can see here from the chart on the right, in our 2 distraction scenarios, we indeed increased the perceived distraction significantly compared to our baseline setup, which kind of verified our scenario composition and our distraction choice here. And then to derive the actual thresholds, we fit a psychometric function to these samples that we got from the experiment, and with this we could derive the upper and lower detection thresholds, as well as the unnoticeability range in between. Here you can see the final plots, and I marked the unnoticeability range for horizontal and vertical redirection here, as well as for gain-based redirection. And we derived these thresholds for all 9 different conditions individually, as well as for the 3 redirection types, by combining the samples of all 3 distraction scenarios to get a more robust estimate using the tripled amount of samples. And when we look at the 9 different conditions here at this slide, I summarized the unnoticeability ranges. And when we compare horizontal and vertical hand warping, we can see that the range is around 9 degrees, and it's very similar and in the same order of magnitude for both dimensions. Also, when we compare the different distraction scenarios, we can see that the range is around still 9 degrees, and the same order of magnitude is present, which is kind of surprising, because here, although the distraction increased, we do not see a substantial change in the thresholds in our experiment. So to sum up our thresholds, in general, we found 4.5 degrees in each direction for horizontal and vertical hand warping to go unnoticed when users really pay attention, which makes a range of 9 degrees. And for gain-based redirection, we found that the user's real hand can be redirected to move up to 13% further or 6% less far than the virtual hand without users noticing. I think this is an interesting finding, especially for haptic retargeting applications. And at the same time, it also kind of indicates that users seem to detect an accelerated hand better than a decelerated hand. So as a general conclusion, when we talk about hand redirection, in a very worst case setup where users really know about redirection being present in the application, and when they actually try to detect the offsets, then there still is a certain range of hand redirection that we can apply and that can go unnoticed, but this range is kind of narrow. And our results now show estimates for the order of magnitude of this range. And at the same time, we want to stress that the thresholds are likely a function of the user and the scene and are likely to differ with different users and scenes. But as we only investigated very conservative setups here, we believe that the estimates that we derived here can actually serve as a well-founded and useful lower bound and reference point for researchers and developers. And when we compare our findings to the tolerance thresholds that were assessed in previous work, which were much larger, up to 40 degrees, we have some indication that users seem to detect or seem to tolerate very large redirections, but at the same time might be fully aware of them. And finally, the question now remains, how can we then increase the detection thresholds? In our experiment, we did not see a substantial increase. We believe that this is really because we only investigated this very conservative setup. And although the distraction increased, the difficulty of detecting the hand's offsets was likely not substantially changed. But comparing our work to previous work, we see two potential paths to increase thresholds. And one is, for example, to use haptic feedback at the fingertips as a kind of haptic guidance, which is supported by the work of Abtai and Vollmer very recently. In their work, users felt and saw a haptic edge underneath the finger pad during redirection. And this matching visual haptic stimuli probably convinced users of not being redirected, and so much larger detection thresholds were found. And on the other hand, when we look at Burns' study, we also have some indication that using a stronger distraction, like immersing the user in a game-like setting, or using stronger auditory or visual distractions that catch the user's attention for a longer period of time might also increase thresholds. And we believe that these two paths are worth to be investigated further in future work. And with this now I want to conclude my talk. So thanks, and I'm now happy to take questions.
So we have 1 minute for questions, so I'll let you start.
Hello. I was wondering how these results might apply, or this approach might apply, if you induce a fuller body ownership illusion. So you have quite a sparse embodiment here, just a hand.
Oh.
But if you induce a full body ownership illusion with full body motion tracking or inverse kinematics, how this might apply.
True. So we don't really know. We haven't tested a full body illusion here. We just used a virtual hand representation, as there are many other problems involved if you really do a full body retargeting, because you also have to kind of, remap the hand and the arm in an appropriate way. But so it's a nice experiment actually that we should investigate in future work. Yeah. Thanks for that.
Okay, so in the